All right, everybody. Here we go. This is the ultimate Axiom overview. We're going to be taking a look at pretty much everything you need to know about Axiom, and then we're going to be diving deeper into specific topics and use cases and more advanced examples. Let's put down a Axiom source shape. You can see we have a few Axiom tools, but the most used one is going to be the source shape in this example. Let's plug it in, and we have our first Axiom simulation. That's great. Let's, I will change just a few things for convenience sake. This, servants, so we get a bit nicer results here. There we go. Okay. So let's take a look at the Axiom source shape. This is something that you're going to be using quite a lot, but you can also bring in your source, your custom VDBs. So if you're familiar with the Pyro workflow, Axiom is going to take all of the naming conventions of Pyro and use it. Although Axiom does have a few specific naming conventions that we will talk about soon. So with the sourcing, right now we're sourcing density, temperature, fuel, and no pressure. Pressure is essentially an expansion. Put this to 100. So if I put pressure to 3, if I put it to 10, you can see it's gonna balloon up. And if we go back to 0, it's gonna dial down. So pressure would be called divergence in Pyro. So it's going to give you that explosive element that you will need later for your simulations, especially for explosions. We have a few different types, like source, influence, collision, and so on. We will take a look at all of them, and we can also change the shape. So you can put it to a pyramid like this. Now you can see the source shape takes an input, so you can take in a test toy or Flippy here, plug him in, and you will see that it's not going to take its shape, but it will try to adjust to it in terms of rotations and things like that. Keep in mind, these are just the primitive shapes to make everything faster. If you want your Flippy to actually be a source, so you need to convert him to VDB from polygons, make density out of him, and plug this here. Now this won't work because we are missing temperature. To get temperature, in this case, you can just easily rename density to temperature, merge them, source them together, and now your Flippy is your source. So like I said, all of your Pyro workflows, we're going to be taking a look at quite a few examples, but everything is going to work. Let's plug in our basic source shape, and I will disable the input. So we're back to our triangle, and let's actually, I like the sphere a bit more. All right, so what else we can do here? You can obviously transform it, use a bunch of noises here to make your emitter a bit more interesting. So if you use a noise here, you can see this is gonna multiply a noise and it's gonna break the sphere shape. I won't use it in this example, but you know, if you need to use it, go ahead. You can also deform with the noise, so that will give you even more interesting shapes, which is pretty cool. And then the most basic one is the velocity noise, and it's just going to add some initial velocities to your source. So let's say if we go to 20 and maybe put this to 0.5, we get something that looks a bit more interesting, and it breaks up our shapes. Cool. We also have forces, so Directional is going to be the most visible in this case. Like so, it's just going to push everything up by quite a lot. We can use this, leave it to 10. Something like that looks pretty good. So let's see how the influence would work. Let's rename this to emitter influence, and let's merge the two together. I will disable this and put this to a spin force. Let's take a look. You can see we got a little arrow happening here, and let's change this to an influence. So we're going to have a change in color, and let's put this to a cylinder. I will make this a bit bigger, push it up like so, maybe even a bit bigger. So now our influence, we are only sourcing in, you can see we don't have temperature, fuel, or anything. We are only sourcing in the velocity, and the influence fields are going to be controlled here. So if I put this to 0, nothing will happen. But if I put this to 1, our influence is going to start affecting it. Now that's a bit too much, so I will put this to 0.3. So you get like a tornado type of force happening here. You can also, instead of a spin or anything, any velocities, we can bring in a different type of influence. Let's go back to a sphere. Make it a bit bigger. Push it up. So you can start influencing the fuel, temperature, or pressure. Let's take a look at pressure. So let's put this to 3. You can see when it hit our sphere here, maybe let's go to 1, the pressure has increased, which means that it started to balloon our smoke a bit. You can also animate these values or animate the position coming in and out, which will give you a bunch of different cool effects. Now, all of this is good and great, but let's see how we can do that with a custom emitter. So right now we are still using the source shapes, but we can just as easily go down a sphere, make it a bit bigger. Let's borrow this VDB from polygons here. We do need to change the density to influence, and the influence field is going to act as a mask or as an activator for all of our influence forces here. Without the influence field, nothing will get activated. So we also need a pressure field. So let's rename our influence to influence pressure. And that's also the naming convention. You need the influence and the influence pressure field. That would go this, it would be the same for influence vel or temperature and so on. I'm going to put a cheat sheet here later with all the naming conventions for you, but we will go through all of them, so don't worry. So we have this. Let's merge it together, and we should be expecting something similar to what we had before, but instead it's sucking everything in. We do need to invert our pressure. The Axiom source shape is doing that for us, but in this case we need to invert the pressure so it's pushing everything outwards. So let's create a volume wrangle. Let's say multiply equal -1. And now the behavior is going to be the same. It's going to be pushing everything outwards like we had before. So like I said, the naming convention, if, for instance, we did this, but for temperature, it would still work. So if we plug this in, and now we say, well, we need more temperature, you'll see temperature will increase. We can also have negative temperature. So when we hit our sphere, the temperature will change to negative, and it's going to give you a dry ice type of effect. We can also animate this now. So transform. Let's put down a null here. Bloop. Here we go. Animate. More animation. All right, let's see. Yep, it's not, it works, but we just missed it. So let's change the nice. And now you can also add pressure. So I'm doing random stuff right now, just so you guys know. But just so you see how the fields are working. That's pretty cool though, right? So we have expanded our volume and added negative temperature to it. We can do the same thing with velocities. Let's take this. And let's animate it before, just so we generate some velocities. Let's put down a point SOP. Compute from deformation. So this will give us velocity fields, as you can see. Plug this in. We still need an influence, but now we also need a velocity field. And we're going to call this influence vel. Let's plug this in. Let's reset all of these values and let's give 10 to velocity. Maybe it's going to be too much. I'm not sure. Yay. All right, so that works. So you can see that almost looks like a collision. It's not, it's just pushing everything out with a velocity, but it kind of looks like a collision. So to actually make a collision out of this, and it's usually a good idea to have, even when you have collisions, you can also add pressure to them. You will see, like I said, we're going to be diving deep into this. This is just the basic kind of overview for now. So if you want collisions, let's do the same thing, but instead influence, we would call this collision. And here we would say collision. Oops, still copying the pressure. Collision vel. Plug this in. You can see now our collisions are working, plus R. Let's actually animate this a bit further away. Or am I doing something right? Yeah. All right, so that's how you would do collisions. Now with collisions, you have a few fields here for velocity, and you can also add temperature. Hey, it's me. Sorry for interrupting, but it would mean a lot to us just now if you would leave a comment or like the video. Just helps with the algorithm. You can type anything. You can type Axiom, what's your name, what city you're from. It will help people find this workshop. And if you're truly getting value from this video, consider subscribing to your collision if you wish. So to do that, we would name collision, and we would call it collision temperature. Merge them, plug it in, and let's go crazy, just so we can see how it's working. can also go negative. And you can see the type of effect that it's going to have. So it's either going to push everything down. I usually normally don't use temperature with collision, but you can. This is going to be a bit too extreme, I guess. It's going to be pushing everything up. But just so you know, that also exists. All right, so let's take a look at how we can add collisions with our Axiom source shape. It will be pretty much the same as what you would expect. You would set it to collision. In here in velocity, I'll put this to a bit lower, and we have temperature here as well. Let's put this in the middle, plug it in, and disable this so you can see we are colliding now with the influence sphere. And same thing, you can add temperature. I think, did I set it to 0? No. Temperature, oops, yeah, just needs a bit more push, or you go negative with it. It's gonna feels like it's afraid of the sphere. And then positive. We also have, like I said before, different types. So you can set this to async. It's just gonna erode everything. So that's a good way to remove density where you don't want it. We can also set this to a pump, and let's change this back to a box. So it's not too big. What the pump will do, it's gonna pre-activate the areas that we specify. So right now this is running a sparse simulation. So we're not wasting any resources. Everything is contained within the areas that you see. But if you use an influence, you will see our voxels are going to get much higher from the beginning. And the sim will also get a lot slower because we are now pre-activating this bounding box. I almost never use this, but just so you know, it's here. And then we also do a camera frustum, and it's going to do what you would expect it to do. You plug in a camera, and it's gonna, like if we go outside, let's do a camera, something like this. Let's copy the camera location, bring it in. So you can see now the camera was here, and it's going to be cutting based on that frustum. So it's applying a sync, but based on the camera. Also quite useful for a lot of optimizing and time management. All right, I believe we took a look at everything we can do with the source shapes and how to add some basic emitters with our VDBs. Now let's take a look at the actual settings on our solver. As you notice, we haven't been touching this at all. It was all just what's coming inside the solver. And that's very important. An important point that I would like to make, that the emitter is almost as important as all of your settings here. So when we're going to be looking at some explosion emitters, the emitter itself will shape your explosion, and that's a very important thing to keep in mind. All right, so we're back to our basic smokestack here. Square one. Let's get through the main tab first. So start frame, I think that makes quite a lot of sense. It's gonna start at frame 10 now. Not a lot to explain here. Substeps, we're gonna be taking a look at that, especially with fire. You want some more substeps, just so the solver. Substeps are essentially these guys. What's happening in between the frames. And if you set more substeps, that's how the solver will calculate in between the frames, and it's going to give you more precision. It's well used for fast moving emitters. So if this was animated and it was going super fast, we need the, we're on to Z. Let's go faster. You can see you get some of the stepping happening in between. If you increase the substeps, that stepping is going to be gone. So that's the case where you would want to use substeps in fast moving emitters. Okay. Go back to 6 with this. Just if you guys are wondering, when I'm resetting the simulation, I just press Control and up arrow. That's how I get back. And I think we need to, oh yeah, let's go back to 1. There we go. Kind of want more pressure, just so we get a nicer, more fuller smokestack. Let's take a look at it like this. All right. Mode, I'm almost always in reflection single step. You can change it to traditional as well. More details on that is in the documentation, but it's not going to change this result that we have here by quite a lot. But I like the reflection single step. That's what I would recommend. Division size, it's going to be how many voxels we're going to have. So if we go to something like 1, it's going to be less voxels. If we go to 0.5, which is the default, we're going to have a bit more voxels, and you can see the voxel count kind of here. The true voxel count is going to be displayed here under detail. Under the detail tab, you're going to see we are in fact at 7 million active voxels here, not 2.5 million like what we're getting here. I'm gonna go to 6. And let's increase our pressure just a bit. Just want more volume. Yes. Maybe our temperature as well. So we get up faster. Like it. I like it. Voxels, that is going to specify how many voxels you think you will need, essentially, or that's how many the Axiom solver will reserve. So what does that mean? I'm going to quickly show you. This allocated memory here is how much memory you will need if, oops, go back. Just need to reset it. There we go. Sorry about that. So this is how much memory you will need if we are simming 32 million voxels. If we are like, we're going to sim at least 100 million, Axiom is going to allocate that memory and is going to say, well, this is going to take it around 5 gigabytes of VRAM. Another way to look, at least on Windows, at your VRAM is if you press the window key and G, you will get this performance tab, and I pin it and then I have it here. So you can see right now we are using 29 of my maximum VRAM capacity, and I am using the RTX 3090 in this case. And yeah, that's like 5 gigabytes. So if you have between 7 to 8 or 12 gigabytes, you will be able to sim around 200 million voxels, which is half of my VRAM. If we go to 400 million, it's going to be around 18, I think. 19. And then if I jump to 500, that's going to max out my VRAM. So I can essentially, in theory, sim around 500 million voxels on my GPU right now. So yeah, maxing it out. So you can see my VRAM 100% maxed out. If you don't do this and you say, well, I am only gonna be simming this, that's obviously not true. So let's put a bit more. So what Axiom will do is it's going to be increasing the value here. So under solver, you will see voxel limit behavior. When you hit that limit, it's going to auto increase the voxels by 0.2, which means it's going to be increasing this number intelligently. You can see how it's like, he's like, no, there's way more voxels than whatever you specify. And he's like, oh, I need to increase this. And then it starts increasing. So, but it's good. It's a good practice to allocate that memory beforehand. You're going to have, it's going to give you less errors, and the sim is going to be a bit faster because it won't need to increase the voxels as it goes. Okay, hope that makes sense. If it doesn't, we do have a Discord page with a lot of very talented people inside, and we're going to be happy to have you and happy to help if you join us. We talk about Houdini stuff in general, not just Axiom topics. And then we have our API. So I'm running an NVIDIA GPU, so I'm using CUDA. CUDA will essentially, it's very smart. So what will happen is when you run out of your VRAM, if you do, it's going to start offloading it to your system to your system RAM. So when it runs off of VRAM, it's going to be like whoop, whoop, and it's going to be taking the RAM to your memory and offloading it. So it will never need to switch to the CPU. So that's pretty smart. If you're using OpenGL, it's going to still work with my NVIDIA card, and it's going to work with the AMD graphics cards. The only drawback is that it's going to switch to the CPU once you exhaust your VRAM. And then we also have Metal, and I don't have an Apple computer, but I've been told by Matt and other people that I think the Max M2 Ultra or Max, they have like 92 gigabytes of VRAM, which is just insane. So just imagine how many billions you can sim on your GPU alone. It's insane. So Metal is for Apple stuff, and then CUDA is for NVIDIA. And then here you can specify either your CPU or GPU, or you can, if you have two GPUs, you can select it here. All right, so that's the boring stuff. Let's go to our sourcing. We kind of took a look at this, but let's go over it one more time. So we are sourcing all fields plus velocity. And the basic source fields are here. This tab we looked at was the collision, and then this is the influence. We don't have any influences right now, so this does not work. With velocity, we are currently adding velocity. So we have different types of how to inject the velocity. You can add it, replace, pull, or blend. Pull is a good one, especially for influences. I will show you how that works in a later example. And then here you can change how fast or at a different time, at what time step you want your velocity in this example to be injected in the sim. So frame step is going to be a lot faster than time step. Frame step will do it each frame. So now our velocity is going to go a bit crazy. You can see there's a lot more of it. I usually put this to frame step, and then I push this down here. That will give you a more explosive velocity in general. So that's the sourcing. A good thing to add, see your VRAM here, right? if you enable sometimes your VRAM, if you want to completely flush your VRAM, just disable and enable the simulation here. It's a pro tip. All right, the simulation tab, we have timescale, self-explanatory. If you put this to 2, everything's going to be multiplied. It's going to be all of your forces. You can see our disturbance is going quite crazy. Everything is going to be faster. So this is good for fire. If we do it the other way, we're going to go into the slow motion field. So that's how you would simulate stuff in slow motion. Obviously, you will need to adjust all of your forces accordingly. So now our disturbance needs to be a lot higher, but you can see it will still be in slow motion. Let's go back to 1. What was that? 3? Yeah, that works. All right, so we have something like this. Diffusion, I never use it. It's a blur. Cooling rate is how fast your velocity, your temperature is going to be cooling. In this case, we are not outputting any temperature, but if we go under output, and output temperature, and if we want to visualize it, we go to the pyro bake volume, and let's visualize it through fire. Oops, let's do scatter. Put this to 20 and this to 0.48. Everything is going to be a bit slower now because it needs to generate the scatter field as well. But if we are, let's put this to something like 3, it's going to cool off the temperature a lot faster. So you can see there's only temperature in the beginning, and now if we go 10, more temperature here, and then it's going to cool off. Makes sense. I will stop outputting temperature for now. So that's our cooling rate. I'll put this back to what it was and push our temperature back. You can also diffuse the temperature, which will do the same as what we had here. It will essentially blur out the temperature. If you don't believe me, let's do it. We won't see it now, but it's going to blur it out. .1 is default. That's what I usually use. Buoyancy is how fast the temperature is going to be rising. And if we put it back, let's put it back to 3. So it's going to be rising a lot faster. Gravity is going to do everything that a gravity does. Wind also it's going to do what you expect it to do. It's going to do things that wind would do. Very cool. Let's do a tangent here before we go to the other ones, and let's go to wind. You can see all the fields here have corresponding controls down here. So if you go to wind, you can add more turbulence into your wind. Too much, but you know, here, let's put this to 2. And you can use a control field. Let's put it on the y-axis, and this is about, what is that, like 15 meters tall. So let's say from 5 to 15, don't do anything, and then slowly start adding wind. And if we add more wind, just to illustrate this, you can see we just did this, a curve, and that's how you can control it here. You can also make it very tight, which won't look realistic, but it's gonna give it, that's how, just so you know how it works. Let's go back to 3. Oops, let's put this back to linear. And let's go to 2. So this will slowly be introducing more and more wind, and it's gonna do an arc. Very cool. So now we have some wind. Force is very similar to wind, but it's going to be accelerating over time. So if you put this to 3, and if you don't like how the wind looks, you can then add it to force. Sometimes I use force instead of a wind as well. All right, so now we have a force. Drag is good for a lot of things. And the values are quite strong, but it's just gonna slow everything down. It's gonna make everything feel sluggish, and it's gonna do what drag does. That's what it's gonna do. Viscosity is good if, so let's say now we have 0 viscosity. Well, that's not true. We have viscosity set to 1. If we put it to 0, you're gonna get your basic smoke type of things. If you set it to 10, this would be better for your smoke, cigarette smoke type of effects. And if we add more dissipation, I guess, just to and then we will probably need bigger turbulences. So let's go to turbulence number 2. So 1, 2. Also keep in mind when it's disabled, it's going to disable the controls. Not sure what the scale would be. Let's go 5. Probably a bit too much. Back to 10. Maybe a higher buoyancy. So you can see this is going to resemble like candle smoke or cigarette smoke type of effects. Very cool. Let's see what we did now. Another good point that now that I disabled that I have a higher dissipation is turbulence is going to be scaled by the density. So when your density is becoming lower, your turbulence is gonna, let me flipbook this. Our turbulence, oops. Actually I want to flipbook this one chunk here. So our turbulence is going to be multiplied down based on our density, and that is going to give us a very realistic look. Like so. You can see how naturally it starts slowing down. And a better way to visualize this would be if we add a lot of density here. You'll see our turbulence is going to go crazy because it's being scaled up by that density. So keep that in mind. But also, with turbulence and disturbances, we have specific control fields. So let's go to our turbulence now. Just this guy. So disturbance. Actually, let's do it on this guy. So 10. Oops. Okay, 5. Just bear with me. I know it looks horrible. But what you can do is, there's also a cutoff field for density here. So when the density becomes too low, it will stop disturbing. Similar thing to what the turbulence does. So these areas are gonna stop being disturbed because they don't, this is the last thing you want, is disturbance where you have low density areas. But what we can do is also use a control field and set it to speed. So we can say, if the speed is not high enough, don't disturb anything. So only disturb things that are going super fast. And now everything is going kind of fast, and you know, I'm kind of eyeballing this here. Oh, but you can see how that was working. So it was disturbing only the tip of the simulation here. And that's where you usually want to disturb things when you want to break up the mushroomy shapes. Now, how do we visualize this, the control field? There's a few ways. We have our Axiom volume visualizer. Plug it here. Currently we are visualizing density, but we need to do it on velocity. So let me output velocity. So we're still doing it on density, but here you can change it to vel, and you can say vector magnitude. So now you can start seeing where we are actually adding. This is pretty much the visualizer for our velocity speed now. So you can also say, well, these ranges, copy parameter, paste reference. So this range is now going to reflect whatever we put in here. So you can say, well, I only want to, like, these are the fastest moving, but now we are kind of, let's go a bit more extreme. We're still disturbing, but now we are kind of disturbing only inwards. So let's see, like, yeah, something like this, something like that. So now we're back to disturbing just the shell. And you can see that is giving us a nice puffy disturbance now. It's too much. Something like this would be good. So that's disturbing just the fast moving areas, and you can see how naturally it's then moving into a non-disturbed zone. All right, so that's why we have multiple disturbances and turbulences. Usually we do want to mix them up. So we do another one, and this time it's here. Let's change the block size to ×2. Now the block size is right now tied to our division size, which means that this division size, so 0.06 times 2, it's going to be 0.12. The same thing with this one, but I usually put this one to 1 and I leave this one to 2. So now we have both disturbances working, and you can, again, it's going to be multiplied by the cutoff field is going to be density, but you can also specify your density here again and say, well, actually, I want something like this happening. And again, how do you visualize this? Put down a volume viz, and you say density, density, and you change your values. You can see where you're going to be affecting. So where there's dark, our density is too low already. So maybe we want 1. Something like this. So this is going to give us, maybe put this to 4. It's going to give us a nice ramp. So 1 to 4, where we're going to be actually adding this disturbance now. And then if you want, you can add another one that's a global disturbance. Put this to 4. Probably too much. And the same thing goes for all the turbulences. Everything's the same, all the control fields and so on. We also have confinement, and this will give you, adds small details to the velocity field. Let's go crazy. It's gonna confine everything way too much. This is good for fog or mist type of effects, but you will have to go higher with the division size. So far we've been in quite high division sizes. So if you go lower, you can see we're going to start getting much nicer volumes. Now let me, pro tip, if you're not using any of the fields, don't output them because the simulation is going to be a lot faster. Now the OpenGL starts, the viewport starts chugging a bit, so it's going to become a bit slower. You can see we are now outputting up to 45 million voxels already. The sim is looking good though, but if you want to get the full speed of Axiom back, you will need to start caching your emitters, and that won't be restricted by the viewport, and it's just going to give you the raw speed of Axiom. So you can see it's pretty fast. You can do a lot of iterations this way, and this sim is going to hit pretty fast. It's going to hit like 100 million voxels, which is quite high res. So let's see. Yeah. So this is quite high res, and you can see when we're looking at the cache data, this is kind of the speed that we're at. So we're super high res now. But Axiom has its special look, I would say, that even at lower division sizes, it looks great. Maybe we are adding too much disturbance now. Maybe this one is a bit too big still. But you can see even in this, even in the viewport, the simulation looks quite good. Like, it has the nice small details, it has the big shapes, everything is working quite organically. Obviously we have too much confinement. That was bothering me, the confinement, not the disturbances. So even at smaller resolutions, like right now we're at 20 million, Axiom will look quite beautiful, and you will get nice simulations like this, super fast. All right, so we took a look at the most things that are related to getting you up and running with Axiom. In the later examples, we're going to be diving deeper into other areas. So let's get to it.